Hello class, once again very warm welcome to you. In the last lecture we have started with the Danawitt and the Hardenberg representations, in which we have the brief introduction about the different link parameters and the different joint parameters, and followed by we have studied the rules for assigning the coordinate frames to the different joints. In this today's lecture we will discuss about how to obtain the transformation matrices which defines the position and the orientation of the ith coordinate frame with reference to the I minus 1th coordinate frame. Also, we will see the brief introduction about the forward kinematics problem and inverse kinematic problems. So, first of all, see in the figure, here the ith coordinate frame will be located here somewhere else, and their axis xi and the z axis is shown over here in the paper, and this will be I minus 1th coordinate frame is there. Its origin will be like this here, and its zi minus 1 and the xi minus 1 axis will be shown over here, and its subsequent y axis will be perpendicular to the papers y axis, and zi minus 1 axis will be perpendicular to the paper. Now here our first goal is to obtain this transformation matrices which defines the ith coordinate frame with reference to the I minus 1th coordinate frame. Okay, so that will be bifurcated as this one, A defined in I minus 1, then we will define the B in A, then we will define the C in B, then we will define the I and C, and it will be cumulatively we will obtain these matrices. Now here the simple funda you should remember: screw Z and screw X. As we know, when we have the bolt and the nut system, so when we will rotate the nut, so it will rotate also as well at the same time it translates, okay, along the axis. Funda is screw Z means rotation about Z axis by angle theta I, so that the translation along the Z axis is taking place by distance di, and screw X means rotation about axis x by angle alpha I, so that the translation is taking place along the x axis by distance ai. Now see here, the ultimate aim of this transformation is to coincide the O I minus 1th frame, origin of I minus 1th frame, with origin of ith frame, as well as we have to coincide all its x, y, z axis should be aligned with the should be in alignment with the other system. Okay, means xi minus 1 axis should get aligned with xi, zi minus 1 axis should get aligned with zi, and ultimately y and y minus 1 will get aligned. Now here the rotation about z axis we have to perform first by by angle theta I. So first we will rotate this frame about this axis zi minus 1, so that xi minus 1 axis will acquire the new position because of its rotation by angle theta I, and xi minus 1 will be now regarded as xa axis, and zi minus 1 axis will be regarded as za axis. Okay, and its origin now will be regarded as O suffix a. Now we have to, because of its rotation, the origin O suffix a will get shifted by distance di, and it will acquire the new position, and that will be regarded as O suffix b. Now the new xa axis will be regarded as xb, new zb axis new za axis will be regarded as z suffix b. Now we have to do the rotation about xi minus 1 axis, or the rotation about xb axis by angle alpha I, so that the zb axis will acquire the new position, that is z suffix c, and the z suffix c axis will be parallel to the z suffix I axis. Okay, so the new z suffix c axis will be there, x suffix b and x suffix c axis will be the same. Now because of its rotation about xb axis by angle alpha I, that is a link twist angle, the translation is taking place along xb or the x axis by distance ai, and ai you know that is a length of the link, so it will get translate over here. Now the zc axis will become equal to zi, there they will get aligned. Xc axis will get aligned with the xi axis because xc axis and the x axis are now collinear one, and y axis and the zi axis, y axis and the y I minus 1 axis will get aligned also. Now as a result of this, these are the 4 rotation matrices we got, rotation about z axis. So this first term will have the matrix of 4 by 4 order, in which first 3 by 3 order will represent the orientation, and the last column first 3 element will represent the translation elements. In the second one, it is also 4 by 4 matrices, it is also 4 by 4 matrices, it will also be 4 by 4 matrices. So as a result of this, we will get the final solution as this one: cos theta I, cos theta c theta I means cos of theta I minus sine of theta I into cos of alpha I, sine of theta I, sine of alpha I, a suffix I into cos theta I, sin theta I, cos theta I into cos alpha I, minus cos of theta I, sine of alpha I, ai sin theta I, 0 sin alpha I, cos alpha I, d suffix I, 0 0 0 1. It will be the final equation that we are supposed to obtain, okay, when we are dealing with the 2 coordinate frames only. When it will get multiple frames will be in the action and we have to do the multiple transformation, this matrix will become more complicated. Now here we will see a simple problem. 2 link manipulator means it is a simple 2R planar manipulator having the 2 links. One is having the length L1 and second link is having the length L2. The link 1 is having the orientation with reference to the base coordinate frame as theta 1, and the second link is having the orientation with reference to the first link as theta 2, because the motors we have mounted over here M1, this is the M2 motor, and here the end effector element will be there. Now how to, first task our is how to assign the coordinate frames at the different joints. Now here the 2 joints are there mainly. Joint 1 where the motor 1 is attached, it's a joint 2 where the motor 2 is attached. Now joint 1, at the joint 1 our rule is if it's a revolute joint, z axis should be parallel to the axis of the pin. So z axis we have drawn over here, that is being perpendicular to the plane of this paper and coming towards the observer, okay, and it will be its x0 axis, it will be its y0 axis, and z0 axis will be perpendicular to the paper and coming out from the paper towards the observer. This will be the frame 1. Why we are giving the x0 over here? Because you have to define the link length, we can show the x0 over here also, but if we shown over there, we cannot define the length of the link, this length of the link L1, and you know that length of the link can be obtained along the x-axis, okay. The frame 2 where its axis is x1, y1 and z1, the same kind of frame is there, just it is being shifted over here, and their rotation about z1 axis is done, and it will have the new orientation x1 and y1 and z1. And the tertiary frame is there, that is x2, y2 and z2. That is just to define the position orientation of the end effector if we attached over there. Okay, now with the help of, after assigning these coordinate frames at the different joints, we have to draw the DH table, DH parameter table. So the table will be like frame 1 and 2, in which the different parameters are there. These two parameters are related to the screw Z, rotation about Z, translation along Z, screw X, rotation along X, translation along X. The frame 1 means, what it basically defines, the orientation of the frame 1 with reference to the frame 0 for this joint, and frame 2 parameter means the orientation and the position of the frame 2 with reference to the frame 1 defined for this particular joint. Okay, so if you see, the rotation about the z axis is possible because it's a revolute pair definitely. So the variable will be the theta I, theta 1. Now the translation, the di is a axis, it's a distance between the two x-axis, x0 and x1. It is 0 now because both the origins are on the same link. So the distance between the normal measured along the z0 axis, that is 0. Rotation about x-axis cannot be possible. Okay, it cannot be possible. It is not possible over here, so it will be 0. And the link length is taken along the xi minus 1 axis. Okay, it is taken along xi minus 1 axis and measured along that xi minus 1 axis, so it will be the L1. Okay, so if you go to the basic definitions, you will definitely come to know. And for the frame 2 also, that is defined in 1, theta 2 will be the variable, the di will be 0 because the distance between the x2 and x1 axis measured along the z1 axis is 0. Alpha is a twist angle of the link, that is also 0, and L2 is a link length. Okay, next slide. This will be the final expression we will have. Okay, now in this frame, with the help of this figure and this table, we can define the two kinematics problem. One is a forward kinematics problem and the one is a inverse kinematics problem. With the forward kinematics problem, to define the position and the orientation of the frame 2 with reference to the 0th frame, we can define the transformation matrices over here, that is 2 defined in base, that will be bifurcated as 1 defined with reference to the base, they multiply by 2 defined with reference to the first frame. Now the first frame defined with reference to the B, that will be equal to rotation of the frame about z0 axis by angle theta 1 multiplied by the translation along the x-axis by length L1. Okay, the two terms are there in between, they are not having any significance, so that they will be eliminated over here, and final expression will get over here like this. Means we have to multiply this 4x4 matrix with reference to this 4x4 matrices, and we will have this final term. Similarly, the frame 2 defined in 1 as a transformation matrices, that as a rotation of the product of the rotation about z1 axis by angle theta 2 multiplied by translation along the x1 axis by distance L2, and that they will have the new 4x4 matrices. And when these two matrices will be multiplied together, we will have this final matrices. And here our final goal of the Dynamite and the Hardenberg representations are fulfilled. This 3x3 matrices will define you the orientation of the frame 2 with reference to the base frame, and this 3 by 1 matrices will define you the position of the frame 2 with reference to the base frame. In the earlier problem, simple problem, you have just seen the very simple problem between the two frames. But if suppose the multiple frames are there, then we have to go for the forward kinematics, where the length of the link and the joint angles are known to you, and finally you have to obtain this expression, that is the orientation of the final coordinate frame with reference to the base frame and the final position of the end effector or the last frame with reference to the base frame. Now we can solve from the same by referring to the same example and the same data, we can solve the inverse kinematics problem also. In the inverse kinematics problems, basically you have the inputs like this rotation matrix, these 4 by 4 matrices are given to you, where the orientation and the position of that frame with reference to one specified base frame is known to you, but you have to find out the variables angles. Here the variable angles are the theta 1 and the theta 2, theta 1 and theta 2. So to obtain them, you can refer to these matrices that can be compared with these matrices. So from this you will come to know that Qx is L1 cos 1 plus L2 into cos of theta 1 plus theta 2. Here Q suffix y is L1 sin theta 1 plus L2 sin of theta 1 plus theta 2. So if we square them and add them together, we will have this final matrices solution, and this cos theta 2 will be obtained like this. So theta 2 will remain on the left hand side, and we can take the arc cosine or the cosine inverse of this complete term, okay, and we will finally get the value of theta 2. Okay, now to know the value of theta 1, we have this expression with us, Qx. In this we know everything, only the theta 1 value is unknown to us. So in Qx we can modify it like this expression, cos of theta 1 into rho sine of psi minus sine of theta 1 into rho sine of rho cos of psi. So if we modify this equation like this, so we will get the final expression as rho into sine of psi minus theta 1, and Qy is equal to rho into cos of psi minus theta 1. Okay, so if we have these two values, so we can obtain the value of theta 1 as, we can take their ratio. So actually that will be the tan of psi minus theta 1, okay, we will get now, and that will be finally modified like this, provided that value of rho is not equal to 0. Here the value of rho will be equal to qx square plus qy square actually, okay, under root of qx square plus qy square. So here this today we have discussed about. Now I will summarize this. Now the Dynamit-Hartenberg representation is used to find out the position and the orientation of the any coordinate frame with reference to the base frame that can be defined. And in this today's lecture we have seen the forward kinematics problem and the inverse kinematics problem. In the today's case we have seen the simpler planar manipulator problems. In the further lectures we will see the special manipulators problems. Okay, thank you.